Hi everyone, this is note card number 1. Welcome to AP Calculus. This is your first note card. This note card is on average and instantaneous speed, and I'm just going to kind of go through and give a quick explanation of everything on the top of the note card here is sort of information that you want to know, and then down below is going to be some practice problems, usually between 1 and 4 problems. So I'm going to start on the top of the note card. The first thing that I want you to notice is this word speed. So we're going to be talking a lot about velocity and speed this year, and I just want to make a quick distinction. I think the easiest way to think about it is I want you to imagine that there's a race car track, and here's the start line, and I want you to imagine a car driving around the outside of the track. And let's say the car, this is a NASCAR track, and the car is going 120 miles per hour, something like that. And the car goes all the way out around the track, and it gets back to the starting point. And it's been going, on average, about 120 miles an hour. Now, the average velocity of the car would be 0, because the car started in one position and it ended in that same position. So in essence, it didn't travel anywhere. But we know that speed, its average speed was not 0. Its average speed was 120 miles per hour. So there's a difference between speed and velocity, and mathematically that difference just involves the absolute value bars. So when we're talking about speed, we don't care which direction the car is going. We just care that it is moving a certain speed. So that's what those absolute value bars do. So here we'll go read the definition of average speed. It says average speed is defined as the total distance d traveled by the elapsed time period t. Graphically, the average speed is the slope of the secant line. And then this is the equation for it right here. Now we're going to contrast that from instantaneous speed. So instantaneous speed is the specific instant at a specific instant in time. Graphically, the instantaneous speed is the slope of the tangent line at a specific point. Analytically, we need calculus to determine this instantaneous speed. So right away, note card number 1, we're talking about the need for calculus. And I want to give you a quick example to show you the difference between average speed and instantaneous speed. And so I want you to imagine driving up Independence Pass. So you're down in Aspen, down here, and you drive up to the top of Indy Pass. And let's say that you start here at 8 p.m. and you get to the top at 9 p.m. Now that's not very fast. I'm sure you guys have been up Independence Pass and done a lot faster than that. But let's say Independence Pass is about 20 miles, and it took you 1 hour to get there. Your average speed would be 20 miles per hour. Now, that doesn't mean that you were going exactly 20 miles per hour the entire time. You could have been going 60 right here, and then you might have stopped for 30 minutes to go in the punch bowls or something, and then continued on up the pass. So you could have been going 20 miles an hour some of the time, but you could have also been going 60 miles an hour here, maybe 30 miles an hour here, maybe 0 miles an hour. So average speed doesn't look at your speed at any moment. It's the average over a certain time interval. Now, instantaneous speed is what we're going to need calculus for, and that would be if you drove past, let's say when you were going 60 miles an hour, you drove past a police officer, and the police officer clocked you going 60 miles an hour, and you got a speeding ticket for that. That would be your instantaneous speed. That's your speed at a specific instant in time. that's instantaneous speed. So the difference between your average speed over the course of your hour-long drive up Independence Pass versus your instantaneous speed when you pass the police officer. That's the big difference between average speed and instantaneous speed. And that concept is going to be really important going forward. So the point of this note card is just to kind of tease out the difference between those two ideas. All right, now let's take a look at the example problem. You'll see on some of these example problems, it'll say calc here. We're not going to get to use our calculators very often this first semester, but if you see that calc, it means that you are allowed to use a calculator here. And if you take a look at this equation, you'll see why. Those numbers aren't so nice, and it'll be nice to use a calculator to evaluate that function. Now, number 1 says, a roller coaster has its largest drop modeled by the equation d of t equals 1.93 t cubed, and then that equation goes on, where d of t is measured in feet and time is measured in seconds. So we get d of t, this is measuring the distance that you've traveled over a certain amount of time. A says, what is the average speed of the roller coaster from 2 seconds to 8 seconds? Now, here's a quick visual graph to give you a sense of what's going on here. So if you graph this function, d of t, you'll get something like this. And after 2 seconds, and the corresponding distance you've traveled, or the height, is going to correspond with a point right here. And then you're going to go down that big drop. And at 8 seconds, you will be near the bottom of the drop. And if you graph it on Desmos, you'll see what I'm saying here. Now, you can see that you're probably going some different speeds through that whole time interval from 2 to 8 seconds. And we're probably going pretty fast by the time we get to the bottom. But it's asking for our average speed. And that is kind of like the slope between these 2 points. So if I make 2 points here, the blue point is going to be 2, comma, and I want you to plug 2 into the equation. You should get 274.47. And then the green point down at the bottom there, that's after 8 seconds. Your height should be 20.97. Now, to find the average speed, all we really need to do is find the slope between the 2 points. So let's use the slope equation, which is y2, which is 20.97, minus y1, which is, I'm going to get rid of this part of this graph here, 274.47 divided by 8 minus 2. Now, you can see that's going to give us a negative number on the top, and that's why these absolute value bars are so important. So I'm going to make sure to remember this is average speed. I need to use the absolute value bars and plug that equation into your calculator, and you should get 42.25 feet per second. So your average speed as you do that drop is 42.25 feet per second. B, what is the average speed of the roller coaster from 4 to 6 seconds? So now we're kind of tightening our interval. We're taking those 2 points and we're moving them a little closer together. So instead of 2 seconds, we're going to look at the point at 4 seconds here, somewhere right there, and then we're also going to move this a little closer, and instead of 6 seconds, instead of 8 seconds, we're going to look at 6 seconds. So the math is going to be similar here. Go ahead and find those points. You get 4, 228.37 and 6, 112.99, and then we can do the same slope equation. And now we get 57.69. So 57.69 again, feet per second. Don't forget your labels there. And then number 5 says estimate the instantaneous speed of the roller coaster at exactly 5 seconds. So essentially, this process of moving those points on our curve closer and closer together. So remember we started at 2 and 8, and we're basically taking those points and we're moving them closer and closer together. Halfway between 2 and 8 is 5 seconds. And if we keep calculating the slopes as we bring those points together, we're going to get closer and closer to the speed, the instantaneous speed at 5 seconds. So it looks like as we started moving those points together, the speed actually went up a little bit. And so now let's investigate what happens if we move the points really close together. And I'm going to go ahead and say the blue point has moved from 2 to 4. Let's move it really close to 5, which is, let's move it to 4.999. And then the green point started at 8. It went to 6. Let's move it really close to 5 from the right-hand side, which is going to be 5.001. So go ahead and try to calculate the average rate of change between those 2 points, and that should give us a pretty good estimate of the instantaneous speed. And so if we go through the same process here, you'll get the point 4.99, 173.61, and 5.001, 173.49, and we'll do the same slope equation, and that gives us 60 feet per second. So as we brought those points closer and closer together, which I want you to try in the Desmos activity, we're getting a better and better estimate. And remember, this is still an estimate of the instantaneous speed. We'll need calculus to find the exact instantaneous speed, but this is a really good estimate of the instantaneous speed, and that's about 60 feet per second.